Welcome to the Here's a Summer of Programming Languages. Have you ever asked yourself, am I using a suitable programming language for this task? Then this collection of introductions to programming languages used in research software engineering has something for you.
Welcome. My name is Valentin Churavy and I'm joined by my colleague, Mosè Giordano. We are both research software engineers. I work at the University of Augsburg and Mainz, where I work on the Julia compiler and runtime. My overarching goal in life is to make HPC and GPU-based programming easier and more accessible to scientists, engineers, and everyday users. In my day job, I work with science teams to help maximize their usage of Julia.
I am a RSE at UCL, where I work on many different projects, mainly about HPC, and my goal is to spread the use of Julia in HPC, but also any other field.
Today, we are going to introduce to you the Julia programming language. So maybe what is Julia? Julia is a modern, dynamic, general-purpose compiled language. It's interactive. It's like Python in that regard. It can be used in a REPL or in notebooks like Jupyter, or in a Bluetooth notebook like the one I'm using currently. Julia has a runtime which includes a just-in-time compiler, a garbage collector for automatic memory, all of the creature comforts that you normally have in a modern programming language. Julia is mainly used for technical computing, and it addresses a gap in the programming language for numerical computing that we have seen over the years. The main paradigm of Julia is not object-oriented programming, but it is multiple dispatch. So what functions do depend on the type and the number of all arguments, not just a few. Why do we like Julia? Well, I personally find Julia very explorable and understandable. It is a lot of fun to program in for me. It has composability thanks to multiple dispatch, and we will talk about that a little bit later, what we mean by composability. It has the really neat ability that user-defined types are as fast and compact as built-ins, so there's no special code, no special source. You don't need to drop to a different language to get the maximum performance. You can write code that is close to the mathematics, and you don't need to switch languages for performance. So you can write Julia code, optimize it, engineer it, and get it to be as fast as any other language. But if you already have some code around that you want to reuse, you can call other languages from Julia, like C, like Fortran, even Python these days. It is a free and open source language. It is MIT licensed, so you can look at it, you can tear it apart, you can find bugs and report them and engage with a big open source community on the internet. So Julia purportedly is solving a problem that is deemed the two-language problem, where we as research software engineers and in other software engineering efforts, we start out by prototyping in one language. Most often it is a high-level dynamic programming language that allows me to easily express my ideas. But then once I've done with my prototyping stage, performance forces me to switch to a lower-level static programming language that is closer to the machine, that is more cumbersome to program in. So for convenience, people often use scripting languages, Python, R, and MATLAB. But for all of the hard stuff, they use a system language like C, C++, and Fortran, or nowadays Rust. This is very pragmatic for many applications, but especially when you collaborate, as we often do in scientific software development, it has a few drawbacks. First of all, when we write the hard code that is the one where we spend most of the performance, well, we kind of want to have a language that helps us, that is easier to express and that is easier to introspect, to look at what the code is actually doing. So for me, when I do performance engineering, I don't want to be distracted with the very, very nitty-gritty detail. I just want to focus on the nitty-gritty of the scientific software that I'm expressing. It creates a social barrier, a wall between users and developers. So it creates this dichotomy between the the people who write the scientific software day to day, and then the users who are trying to run simulations, because they are no longer capable as users to express and explore new ideas in that scientific software without learning yet another programming language. Sometimes you also run into a sandwich problem, so we are layering system and user code that can be expensive, and it is nicer if everything is in one language, because then the compiler can help us and perform full stack optimizations. We believe that Julia is a great language for research software engineering, especially because it's tearing down barriers of collaboration. It fosters collaboration. I've seen this in multiple projects over the years, where the scientists and the domain experts are writing code, and I, as a performance engineer, can support them and help them, but I'm never in this situation where I take their code, I go away, spend some time rewriting it in a lower language, and then we lose track of each other. It lowers the barrier from package user to package developer. So when you use a Julia package, or even the language itself, you can just open it up in VS Code, you can look at it, and it's the same language that you're used to, and you can edit it, you can improve it, you can fix it, you can write your own packages very easily. And so this, and sometimes I say Julia is turtles all the way down. So you can start at a high level with very simple Julia code, and then you can look deeper and deeper and discover and explore Julia code bases while sticking in the same language. Sometimes, of course, that we are still calling into C library where it makes sense. And so sometimes, yes, you do see actually, oh, there's a foreign function call to a linear algebra library, but those cases are fairly rare. It also has understandable and explorable performance. So one of the nice things about Julia for me is that I can see what the compiler is doing at all of the stages. And maybe for research software engineers in particular, interesting is that it has a native test framework, and the use of continuous integration is widespread throughout the ecosystem. So testing standards are quite high in the Julia community. Julia is currently at version 1.11, and hopefully soon we will release Julia 1.12. This provides a stable language foundation where the language itself is mostly focusing on foundational improvements over time, but the language is no longer rapidly changing. Based on this stable foundation, there's now a vibrant packet ecosystem, and there's a yearly developer conference that has all of the talks and workshops uploaded on YouTube, and maybe also very interesting for current development strategies in research software engineering. It has excellent native GPU computing support. So, how do we get started with Julia? Well, it's very, very quick in some sense. There is a version manager called Julia App that you can install on every system, which we would recommend, so that you can automatically get new patch releases and new minor releases of Julia installed. If you want to dive into Julia, I wholeheartedly recommend Modern Julia Workflows. It's an excellent website that has resources on many like simple workflow questions. If you have run into issues or questions, there is a active discourse forum where people discuss and engage. And of course, there is thorough documentation of both the language, but then each package often has their own documentation. And there is a community calendar where you can see office hours from various working groups like the Julia HPC or Julia GPU office hours. And so you can join any of these events, of course, and ask questions and engage. Now, what is Julia? So this is a very brief introduction using an example from scientific programming. So we are going to implement the Newton methods in 1D. And so we want to essentially find roots of a function. And so you might have gotten to know that method in high school or in early university. So we have a function f of x, and when we want to find where that function becomes 0, and so we take the gradient of that curve and we follow that gradient, and then we iteratively do multiple steps until we actually find a 0 point. So here we have this, we start at x0, we evaluate the function, we take the tangent line, we get a new point x1, and then if I take an additional step, now we update our value, we find the next point, we do another step until we get to our 0 point down here. And so of course I can also change here the our starting points, and I get slightly different answers. And this is one of the nice features about Pluto in particular. It's very easy to make these kinds of interactive displays that are very useful to do in terms of teaching. And so for a more complicated equation down here, of course, we can also see how the Newton method slowly solves a problem. And here we have seen our first pieces of Julia code. So we have a function f of x, and this almost looks like I've written down some mathematics, and then I'm applying the Newton function over that. And so if we look at how Newton is actually implemented, so this is the gist of the function. We use forwarddiff.gl, which is an automatic differentiation framework in Julia, where we obtain the derivative of f at x. And now we can iteratively solve our problem, and we can say maybe do 10 iterations, maybe do 3 iterations. So this is a very simple Julia function. And now these plots are slightly more complicated. So I'm using a plotting framework called Markey. And Markey, and so the Newton function right now is not just calculating the Newton function, but it's also doing the plotting. And here is basically a little bit more Julia code to look at, where we plot these iterative lines while we go along. And Mosè will now talk a little bit about the Julia package manager.
Yeah, so Julia comes with a built-in package manager, which is a native notion of environments, like in many other languages. And the environment is described by 2 files. One is the project.toml file, is a file which only lists the direct dependencies of your package, of your environment, and also you can optionally specify compatibility. So say, oh, my package depends on package JSON, for example, in this case, but only version 0.21, in case you know that other versions are not compatible. Also, importantly, the package manager follows the semantic versioning scheme. So when there are breaking changes, that's signaled by a change in the major version number. And this is very important when you specify compatibility bounds, because it gives you a very clear way to indicate when there is a new breaking change. You can interact with the package manager here in the REPL. This is an example from the Julia REPL. So you can see the status or add and remove packages. Importantly, also about the Pluto notebook, this integrates with the Julia package manager. So actually, when you have a Pluto notebook and you add packages to your notebook, it's also under the hood for you updating an environment. And this means that you can provide to other users fully reproducible notebooks, because the package environment is automatically checked inside the notebook itself. And the reproducibility and the environment includes not only the Julia packages, but also external packages, which are handled through a framework, a Julia framework called Binary Builder. Which is basically a sandbox for cross-compiling packages. We use this to maintain over 1,000 packages. And this encodes all best practices, including reproducible builds. And repository Yggdrasil is a collection of all the build recipes that we maintain in the ecosystem.
As I mentioned before, Julia provides tools to interact with other languages. And primarily, C and Fortran libraries are very built into the language itself. And so we have a macro called, so if you ever see in Julia a function with an @ symbol in front, that's a macro. It's a function that takes an expression and turns into another expression. And so we have the C-call macro that allows you to call functions in shared libraries directly. And if you want to know more, there's a section in the documentation about how to map types and how to do calling between C and Fortran. If you want to do that for a lot of different functions, you probably don't want to write these wrappers by hand. So we have an automatic wrapper generator called clang.gl that basically parses the C header and then generates the mapping Julia code from it. You can also use the @C function macro to create a callback, so a raw C pointer that you can pass into a different into a shared library as an example, and then call back into Julia from that. But as soon as you interact with a different language, you always have to be careful about GC interactions, and you have to think about who owns which memory and who is responsible for releasing that memory. Julia will do it automatically for you, but C or Fortran will require you to think about this manually. So here's an example from a library that I wrote a while back. UCX.gl. UCX is a message passing library essentially for used in high performance computing. And here I have a function called UCP_put_NB, and I'm using ccall to call this function, and I'm passing it descriptions of what the expected types are. Ought to be, so that Julia can perform conversion to those types to make sure that we are matching the corresponding C, ABI, and C of the shared library. And then here is a more complicated variant thereof, where I have a callback that will be called from the C library itself. And I can create this callback pointer inside my function here, and then I can pass it to UCP put NB as the callback argument, and then later on it will be called automatically, and then we are calling from C back into Julia. As you can see, I have to think about memory preservation, and so it's a little bit tricky, and I would recommend you read the documentation before you get going. Interaction with Python is also possible, and so we have interaction with Conda, so that you can manage Conda and Julia packages together. So Conda pkg, and then I can add the C-born package. And so that under the hood will initialize the necessary stack. And now I can use Python call and take a data set, like the HiRSE data set from R. I can import the C-born package, and then I can use C-born directly here in Pluto in my Julia environment to create a pair plot of these species. And I can also do this pair plot natively in Julia, of course, but I didn't find like a super direct map of this style. So if I like this style from C-born, then instead of writing it myself in Julia, I can just use the existing Python package and not have to worry. But if I did want to write my own pair plot in Julia, there's the pair plot package. And so I can have quite a bit of flexibility about what kind of plots I want to do and how I want to plot them. And so I was trying to match the styles. I did reasonably well, but this is probably, you could improve further to actually then match the C-born style if you wanted to. This is again using the Marquis plotting library under the hood.
Julia is a dynamically typed language. And here is an example of how you can define custom data types. You can have both abstract types or concrete types, which you define with a struct keyword. If it's only written struct, this is a immutable structure. If you want to use a mutable structure, instead you need to prepend the mutable struct keyword. And we mentioned already before that Julia is not object-oriented, but instead uses the multiple dispatch paradigm. And here there is an example of a showcase of how the multiple dispatch works in practice using the rock, paper, scissors game. So here is a example of how you can implement the rock, paper, scissors in less than 10 lines of code without using if conditionals, but only using the type system in Julia. So we define the abstract type of shape, and then the rock, paper, and scissors types as subtypes of the abstract type. And then we define the rules of the game. So we define a method play, which takes as first argument paper and second argument rock. In this case, the paper wins, and then so on, also for the combination of paper, scissors, or rock, scissors. But you also want to automatically define the rule of the tie when you have 2 times the same type. So you can here indicate that both arguments are the same t. So in that case, you automatically define the tie rule without having to specify all the combinations. And the other important rule that you want to define in this game is the commutativity. So whenever you have 2 types that don't match all the previous or the more specific conditions defined above, this method is just swapping the 2 arguments, and then you will match the more specific methods defined above. And so with only 5 definitions, you are defining all the rules, and this is also easy to extend to more types, not just 3. And here are examples instead of actually playing the game. So when you combine paper, scissors, this is one of the methods that we defined above. Rock, paper instead is using the commutativity rule because we don't have a specific argument for when the first argument is rock and the second is paper. And also there is the example of the tie when you have 2 times the same argument. And also Julia has many introspection capabilities. One of these is the which function or macro, which allows you to find which method is being called when you have a function call. And then you can also play with random arguments here and see live what you get. There is a missing comma. So you can play these with random arguments and get different results every time.
We've been talking about the fact that Julia is a dynamic programming language. So what actually do we mean when we say that? So when people commonly refer to this, they talk about the fact that the variables, when you write them down, have to have a type declared. So they're talking about what is syntax. So either in C, I might have to say I have a float x, and in Julia, I would just write x. And then the question is, during the lifetime of the variables, can the types of those variables change? And in a dynamic programming language, or in some dynamic programming languages, that is true, because types are checked and executed, checked during on the fly during execution, and the type of variable can change. In a static programming language, the types are checked before runtime at compile time, and so the types are fixed. But you can also ask the question, well, is the amount of code fixed? So We can compare closed world versus open world semantics. And so in a closed world language, the amount of code is fixed. I can't add any more code. And of course, this is a spectrum. This is a interesting question because in C++, I can load dynamic libraries. So at runtime, I can add more code to my program that was not visible before the execution. And in languages like Julia, you can also load dynamic libraries, but you can also add more code by using evaluate, eval. And so because we can add code, or we can even change code that we have already defined, that is also a form of dynamicism. And lastly, one form of dynamicism that people forget often is about struct layouts. So are data structs closed, well-defined? So can I reason about all of the fields of a struct being laid out in memory in a certain way? Or can the fields in a struct or even in an object itself change while the program is running? And so with multiple inheritance in an object-oriented program, often we have a struct layout that I can extend. I can't necessarily change it, but I can extend it. And so sometimes I need to, I don't quite know what the data layout will be of an object because I don't know that it is closed. And in some programming languages, objects are not closed at all, and I can add fields at runtime. So dynamic semantics really are a spectrum, and as a programming language, we can kind of pick and choose where we want to be. And Julia has a dynamic type system. It has open world semantics, but struct layout is static, but even that is currently changing. So the upcoming version in Julia 1.12 does allow for the redefinition of types. It does not allow for the opening of types. So there is a more complicated mechanism at play here that will hopefully allow you to change the definition, but then you might have to recreate the type at runtime because now you have two types with similar names that mean different things. Because of these semantics, compilation of Julia is an interesting question, or a compilation of any dynamic language is an interesting question. So how can we do actually? How can we actually compile Julia? And just roughly, the compiler stages of Julia are, as in many other languages, we take the text that you write and we turn it into an abstract syntax tree. Then we linearize that abstract syntax tree. We simplify it so that the compiler can reason about it. Then this is Julia specific. We perform type inference over it, which is an abstract interpretation-based algorithm that infers the types of each statement in a function based on the arguments. Then we perform some high-level optimizations that are Julia-specific, and we translate our inferred code into LLVM-IR. LLVM is a compilation framework that is used by many, many people these days, and is also used for Clang, C++, Rust, and some other programming languages. The LLVM then has a middle end where it does target-independent optimization, and then there's a back end that does some target-specific things, and then at the end it emits machine code and executes that on your CPU. So here is what I meant earlier with reflection methods in Julia. We can dump an expression. So here we have 1 plus 2, and we can see that the Julia expression of this is has a head that is a call, 2 arguments, which is the function name, and then the arguments to that function. And then we can analyze this with a code typed. So this is basically after type inference. So we know that what we have at float, and we know that when we combine x and y, we get a float 64 back. And then I can take that, I can turn it into LLVM-IR, and you can see that the Julia add float intrinsic maps to the LLVM f-add intrinsic. And float 64 maps to LLVM's double. And then lastly, this all turns at some point into native assembly. And so I can also introspect the assembly that any Julia function generates. And so you can actually, when you really care about performance, you can figure out what the Julia compiler is doing, or in case the Julia compiler ever gets confused. And you can look at anything from the inferred code to the native assembly emitted by the compiler. But you don't have to, right? This is something that you can do if you're interested in performance engineering, and it's a useful tool, but it is not something that you have to do. Now, because Julia is used for technical computing a lot, it is very important that it has a robust sort of parallel programming infrastructure, and I will give a brief overview over both distributed, accelerated, and multithreading. The most robust implementation and support for distributed computing in Julia is using the message passing interface, MPI. And here in this Pluto notebook, this is a little bit more complicated. So I have a magical @MPI macro that's purely used for teaching. Please don't use it in real work. But it allows me to just briefly show you a couple of MPI programs and execute them within here in Julia. So we have to load the MPI library. And then we have to initialize MPI, and now we can use what the common like MPI primitives, MPI convert, to get our communicator. We can query the rank of our MPI process of this communicator, and then we can perform something like an integral over this expression, which is basically calculating pi. And here we are performing an MPI reduce, where we're summing all of the intermediate values calculated on all of the different processes together into one value, and then we output that. So our error, this is what we're calculating here. We're calculating the pi symbol is the true pi, and our pi calculation is our approximation, and we can calculate the error of doing basically 50,000 steps. And we can also get the partial pieces from each of the individual ranks. So here I'm calculating it with 4 processes. So I'm getting 4 values back, and I can sum them up locally and see that it is roughly the same value. One of the nice things about MPI.gl is that it's not just working with floating point numbers, but it also supports arbitrary like Julia types. So I'm using the static arrays package that allows me to create small arrays of fixed sizes. So here I have I'm creating a 3 array, and now I'm passing it to the allReduce function. And so I'm summing up all of these static arrays. And so this allReduce actually has to be not just the normal MPI sum operand, but it is a Julia operator that adds these 3 values together and creates another S vector out of it. And so there's a lot of flexibility built into it. But you can also use all of the low-level MPI routines to maximize your performance if you want to. Over the last couple of years, Julia has built out a really excellent GPU computing infrastructure based on a couple of composable pieces and a couple of vendor-specific pieces. So at the heart of it, there is a package called GPUcompiler.gl, which takes native Julia code and compiles it directly to GPUs. Then we have a package called GPU arrays, which provides high-level array-based common functionality. So in case you're trying to do a matrix multiply of something that your vendor does not support, there is a fallback implementation in GPU arrays that we can probably use. Then there's a package called kernelabstraction.gl, which provides a vendor-agnostic kernel programming language. So if you feel the need to drop down to the low level and write a bespoke kernel for your problem, you can use kernel abstractions for that, and still be vendor-agnostic. And then there's adapt.gl, which is a very small Julia package, but it allows you to basically translate data structures between the CPU and the GPU, and between the GPU host view and the GPU device view. And so it's quite useful when you have more complicated state. All of that is then supported by a suite of vendor-specific packages, so CUDA.gl, AMD GPU.gl, OneAPI.gl, and Metal.gl. Metal.gl is for Apple GPUs. OneAPI.gl is for Intel GPUs. AMD GPU is, of course, for AMD, and CUDA is for NVIDIA. And these are in various states of development. So CUDA.gl is the oldest, most stable, and most widely used one. And Intel, OneAPI, and Metal are the two younger ones. And AMD GPU is somewhere in between. And so you can write vendor-specific programs using also vendor-specific functionality, but you don't have to. You can use kernel abstractions to be a vendor agnostic. But these packages essentially interact with the GPU drivers and the vendor-provided libraries like Q+ or Rock+, depending on your vendor. So just a short snippet here is we have a vendor-specific GPU kernel using CUDA, where we use the CUDA intrinsics to calculate our grid position. And then we operate our kernel. And then we use the add_CUDA macro from CUDA.gl to launch this over a set of threads and blocks. So this is very close to or similar to CUDA C++, of course, with some complexities removed. And in kernel abstractions, this looks very similar. Now I have to annotate my function saxpy as a kernel function. And instead of using the intrinsics, I have an add_index macro. But essentially, this is the same thing. But I don't need to go to this level to make use of my GPUs. I can also just use array abstraction like Julia's built-in podcasting to express the same operation. And these kernels are actually the same speed. So sometimes it is not, often it is not necessary to write your own kernels. So how to use kernel abstractions? You have to write an add_kernel function, and then you can allocate memory on the target backend. So you want to allocate a Q array or a rock array, and then you can instantiate the kernel for a specific backend, and then you can launch the kernel over a grid of points. And so the add_index macro gives you essentially for each of the ND range points one of the elements. One thing of note is that, of course, the GPU is performing its computation asynchronously to the CPU. They are ordered with respect to each other, but when you access a GPU data, it will be synchronized on access. But if you're doing any benchmarking, you have to do the synchronization yourself to ensure that you're not just measuring the launch of the kernel. The high-level array-based programming infrastructure for GPUs, you can think about it as all kinds of data pair statements like map, prod, recast, scan, and reduce. These all map very naturally onto the GPU execution models, and so they're just implemented and provided. But using multiple dispatch and specializations, we can write reusable applications that can target multiple GPU vendors without having to change your code that much. And then, of course, we expose array-based libraries like PLAS and FFT to the user as well. So I mentioned these array types briefly before, but they describe where memory resides, and where the memory resides decides how the code is going to be executed. And so the program is following the data, not the other way around. This has the nice property that data movement is explicit, and in most GPU situations, the data movement is the most expensive part of the program. And so here we have the CUDA data type, Q matrix, rock matrix, and depending on where I allocate it, my program is going to be executed somewhere else. So when we talk about portable programming, we should maybe specify what portability means. For me, the most crucial aspect is, can I actually just run on a different computer architecture? So this also includes different CPU architectures. Sometimes programs are so specific that they can only execute on Intel CPUs. And we live in a multi-GPU vendor world, so I want my programs to be a priori capable of running both on an Apple laptop and also on an NVIDIA-based supercomputer. Besides just being able to run, I probably care about the fact that the answers are the same. So I should get the same. The program should compute the same thing despite running on different hardware. Because otherwise I cannot develop on one platform and move to another later. So I might be writing a program on my laptop and then I want to go to a supercomputer, and if I can't trust that I'm computing roughly the same thing, then I can't do this development workflow. Less importantly, but still quite importantly, is does it achieve the same performance? And this is a constant topic of debate. So there you might see that some kernels perform better on one hardware generation from one hardware vendor, and then the next hardware generation for the same vendor or from a different vendor, performance characteristics have changed, and so you might need to rewrite your kernels. That is something that is really hard to solve, and we are not claiming that we have solved it. So you can write portable kernels, but the performance of said kernels might differ depending on which generation of GPUs you're using. And lastly, despite writing general code, I do want to take advantage of platform-specific capabilities, because otherwise, I don't want to have a regression to the mean. And so this is really where the multiple dispatch of Julia comes into its own, because I can write a generic program and then I can specialize parts of it on the fact that I'm executing on an NVIDIA GPU, and I can use NVIDIA-specific capabilities that I don't have elsewhere. Just as a brief note, adapt.gl is a very lightweight dependency, and it solves the question, well, I have a data type like the adjoint of an array, and I want to move it to the GPU. How do I do that in a generic fashion? And so I can adapt my complicated structure to a Q-array, and I get back a complicated structure of a Q-array instead of an array. If I want to do that for my own data types, I have to implement this interface called adapt structure, where I just basically reconstruct the model and call adapt on each of the fields of the model. For that, I do also have to make my fields, my data structures parametric, so that I can actually do this exchange. Julia also has shared memory parallelism, so using multiple threads on one machine. But Julia is task-based, so we have end-to-end threading, green threads, and you have access to channels and logs and atomics. And so here is a very simple parallel program to calculate the series of Fibonacci sequence. And here I'm using the add spawn macro to launch a task. And then I later fetch a result from that task and use that in my computation. So this is what we mean when we say Julia is task-based, but often I just want to make a for loop parallel, and so there's also the add threads macro that allows me to parallelize for loops. And here I have a prefix sum implemented in parallel. There is a package that has come about, I think, about now almost a year and a half ago. That is called Oh My Threads, which provides a very user-friendly interface going behind just these simple add threads macros. So if you want to do some more complicated things, it might be quite worthwhile taking a look at the Oh My Threads package.
So now we talk concretely about what we mean by composability. So here is an example of plotting the solution of a differential equation, which includes numbers with uncertainties and units. So we can see that here we are loading multiple packages. Measurements is a package for defining numbers with uncertainties. Unitful is a different package for defining numbers with units, physical units, and instead ordinary TSIT5 is part of the big ecosystem of differential equation solvers in the Julia ecosystem using a specific solver. And yeah, so here we are defining some important quantities for our problem, like the half time and the mean lifetime of the radiocarbon. in years. So we are specifying the quantity with both the uncertainty plus minus 40 and the units, years in this case. And then we set up the differential equation, defining the initial quantity and the time span over which we want to solve the differential equation. Again, always specifying units and uncertainties where necessary. And in the end, we define the problem. So we define the function which describes the differential equation. And eventually, we can just call the solver to get the solution of this differential equation. And you can see that in the data frame above, you can see both the units and also the uncertainties for the solution, which is quite nice. But importantly, all these packages, the ordinary differential equation, measurements, and unitful don't know anything about each other, but they are all of them using the interface of numbers, like defining numbers and doing addition, multiplication, like the basic algebra of numbers. And you get the solution of the differential equation. You can also plot it, and you can, if you switch between only the numerical or only the analytical solution, you can see all the results are basically the same. And you can also plot the error to see how the error of your differential equation goes with time. And yeah, that's it. Another example of defining a custom data type is, for example, stochastic rounding. So stochastic rounding is an interesting concept because when you do operations with real numbers on computers, you basically are actually using a subset, a finite subset of the set of real numbers R. So we can call this set F in this case. And the computers normally use what's called nearest rounding. So whenever you do operations on computers, so using this subset of F, you do some operations, you get a true result, but this is eventually rounded to the nearest, deterministically rounded to the nearest number in F. But you can think about using instead a different strategy. So instead of deterministically always round to the nearest number in F, to your true result, you can round with a certain probability. And for one example of this is rounding down with a certain probability p, or rounding up with a probability 1 minus p. And common choices for this probability distribution could be, for example, 0.5, 1/2, or more interestingly, a probability which is related to the distance to the two numbers. So this is called, it's a strategy for stochastic rounding. In this case, with this probability distribution, basically we want to round more frequently to x2, which is the number which will always be rounded using the deterministic nearest rounding strategy. But also with using this stochastic rounding, sometimes we round down to x1 with a lower probability, but still this sometimes happens. And stochastic rounding is very useful because it basically can reduce the error introduced by the bias introduced by always rounding to the same number in the same way. And this is especially important for low precision floating point number operations. Like in Julia, we have the float 16, but nowadays there are also even smaller data types for floating point operations. And stochastic rounding gives you the statistic probability that the expected result of your operations is actually the true result and not always the approximated result. And again, this is most important when you use low precision floating point numbers. And here we have a case where we want to do this. We are defining a array of 3,000 times the number 0.9 in half precision. We use the naive sum of like the naive summation of all the elements. But if you do this on CPU, you get the result of 2048. And this is because the machine precision of the number 2048 in half precision is 2. So when you try to add 0.9 to this number, you always are adding in practice 0. And yeah, so if you try to plot the accumulated error over all these summations, you see that at some point after 2048, you just your error just grows arbitrarily because you're not adding anything. And our colleague Milan Klawa created a package called stochastic rounding, which basically define a custom data type, this float 16 as R, which implements the algebra of stochastic rounding that you can emulate on CPU. This is very important because actually stochastic rounding is available on some specialized hardware like the graph core IPUs and also some other GPUs nowadays. But you need this specialized hardware to use this ability of using stochastic rounding. Instead, in Julia, you can easily define a custom data type that you can use for exploration also on CPU. And yeah, we can just use the same function that we defined above. We're not changing the function, but we are only changing the types that we are passing to the function. So in this case, it's an array of different elements, this float 16R. And yeah, so if you compute the naive sum multiple times, you get different results. But importantly, they are all of them much closer to the true result compared to the always wrong result that you get with the nearest rounding. And here we can see, like we plot 5, I think, different summation of like repeating the sum for five different times, and you can see the accumulated errors over time, which has a distribution. But again, the error is always much smaller than in the case of always using the deterministic rounding. You can also do some statistics, like you can see that the extreme of the distribution is between 2500 and 2800. The mean is pretty close to the expected result of 2700. There is a standard deviation of 30, and the median is actually exactly 2700. And we can also plot the distribution, and we can see that the nearest rounding is always very wrong and very far from the true value, which is a yellow line. And then the stochastic rounding is as a distribution because we are repeating the experiment multiple times. But importantly, the distribution is centered around the true value instead of always being very far from it. And yeah.
One of the questions we get quite a bit about Julia is, does it have any form of static compilation? And the answer is has always been it's complicated. So for the longest time, there has been a package called a package compiler that allows you to essentially compile all of the packages that you're using into native code and bake them in. But this always resulted in quite very large binaries, and it took quite a long time. And so for Julia 1.12, there is initial and very experimental support for static compilation or for small binaries. And so this is an example from the community that I picked up. And here we have the FHIST package, and we want to provide a binary to that function that we might be able to use in Python. And so we define a C-callable function with all of the like C-typed arguments. And so we take the inputs that are C-typed and we convert them to our Julia arrays. Here is one of those points, again, we have to be careful about memory management. We don't want to take ownership over this array because the person passing us this pointer is responsible for the array. And then we can just call our functions and go from there. And so now how would I compile this? Well, if I have Julia 1.12 already installed, I can compile this project. I can use the Julia C Wepper script that allows me to do so. And I tell it I want to output the shared library. I want to compile the C-callable entry point. I have to acknowledge that what I'm doing is experimental. And then I want to trim the binary down to a smaller size. these that then allows me to create a binary that I can call, from example, from Python. So now I have a libsum shared library that I can pass and use Python C-types library, describe what are the types, and then call it from within Python. So that is nowadays possible, but it is still very, very early days, and you might run into sharp edges. So it's probably not the best part to learn to get started with Julia, but we hope that more and more of these kinds of things will happen over time. So if you want to get started with Julia, the community I have found is quite welcoming. We host a yearly developer conference. It's usually in late July. And you can find more details about juliacon.org. This fall in 2025, there will be also a local event in Paris. And all of the talks of that conference and its sibling conferences are recorded and online on YouTube. So on the Julia Lang YouTube channel, you can find all of the talks going back over many years. And we also have workgroup meetings, as I mentioned earlier. You can look at the community calendar when they are, and there are many different ones. Mosè and I organize the Julia GPU and Julia HPC workgroup meetings, as an example. And these are community driven, so anybody can come and say, I really want to push Julia forward in one area. And if somebody else is interested, you can put a community event onto the calendar and have a regular conversation about it. In case you're just looking for some online spaces to communicate, as I mentioned, there's a Discourse, but there's also a Zulip and a Slack available for chatting and discussing Julia. So you can look at the community channels and choose the one that is right for you. So if you want to continue on your Julia journey, here is, as I mentioned, the Modern Julia Workflows page. That is great. There is the Julia documentations. And over this last few months, I hosted at my local university course, 2 hours per week for research software engineering, and there's a lot more material and more Pluto notebooks on various about topics relevant for research software engineering. So thank you, Mosè, for joining me, and I hope you now get to enjoy JuliaCon.
Thanks.
Thank you for watching this introduction. Please check out the slides on Zenodo, linked below, and see you next time.